All right, this example gives us a really simple circuit. It's got just a resistor connected in series with an inductor. The value on the resistor is 100 ohms, and the value on the inductor is 50 millihenries. And we're going to be asked to find some things like what is the voltage drop across the resistor, what is the voltage drop across the inductor. We'll call that V sub L. There's also a current flowing from the resistor to the inductor. We'll call that I. Now I'm combining examples. If you're following along in the textbook, I'm combining examples 9.6 and 9.7. 9.7 is also going to ask us like what is the total voltage drop across the entire circuit. So the one last bit of information we're given is actually the value of the current. We're given it as a steady state sinusoidal current, 50 times the cosine of 1000 t plus 45 degrees. And that's in milliamps. And we'll just kind of go down the laundry list of things that it wants us to solve for. Part A asks what is the impedance of R. Now we know from the previous video that for resistors it's really easy. The impedance of R is just equal to R. So our impedance, Z sub R, is just equal to 100 ohms. Next up, part B asks us what is the impedance of the inductor. A little bit more complex, but not that much more complex. The impedance of an inductor is equal to J times omega times the inductance. Now remember from our problem statement here, our omega there, omega is equal to 1000 radians per second. So what we'll do is plug all that in. We'll say that Z sub L is equal to J times 1000 times 50. It's millihenries, so we'll say 50 times 10 to the negative third. It's given in ohms, by the way. All impedances are given in ohms. And we'll calculate our final answer here. Z sub L is equal to J. 1000 times 50 times 10 to the negative third is just equal to 50. So J, 50 ohms. Now, part C asks us to find the phasor form of our current, I. So we know that our current I is given us in the statement. I'll just write it out again. IT is equal to 50 times the cosine of 1000 t plus 45 degrees, and that's given in milliamps. And we've got all the things we need to make that a phasor. So we know that I is just equal to 50 at an angle of 45 degrees. And that's in milliamps. Now the milli translates only to the absolute or the maximum amplitude, so we could also just write that it's equal to 0.05 at an angle of 45 degrees, and that would be in amps. So that's another sort of alternate solution. Both of these solutions are correct. Part D asks us to find the voltage drop across the resistor, VR, is equal something. And we remember from our previous lecture, the video we just watched, VR is just equal to the impedance of R times I, which is equal to just R times I. So what we're going to have is this, that V sub R is equal to 100 ohms times RI, 0.05 at an angle of 45 degrees. So all we have to do is multiply 100 by 0.005, and we'll get that our V sub R is just equal to 5 at an angle of 45 degrees, and that's in volts. Moving right along, part E, we're on part E now, is what is the voltage drop across the inductor? Now, we remember that our voltage drop in the inductor, the relationship here, V is ZLI, is given as VL is equal to, remember it was, what, J omega L IM at an angle of phi degrees. Now remember, to get rid of the J, we want to go ahead and actually use the other form that we talked about. Remember this form that I said I kind of liked a little bit better. So say omega L IM at an angle of phi plus 90 degrees. So this is the form that we're going to use. We'll plug all of that into our equation. Our phasor V at L is equal to omega, which was 1,000, times L, which was 50 millihenries, so 50 times 10 to the negative third, times IM, which was 50 milliamps, so that's also actually 50 times 10 to the negative third, and all of that at an angle of 45 degrees plus 90 degrees. So crunch all of that in. 1,000 times 0.05 times 0.05 is going to give us a phasor voltage of L as 2.5 at 135 degrees. So there we go. That is our voltage drop across L. What I'm going to call part F, this is actually where we get into the next example in the textbook, but I'm just going to call it part F, wants to know what is the voltage drop across the entire circuit and it wants it as a phasor, by the way. So as a phasor, remember KVL means we just add them all up. So that's V is equal to VR plus VL. So we'll say that our phasor V is equal to, what did we get for VR? 5 at 45 degrees. 5 at an angle of 45 degrees, and that's in volts, plus, we've got it right there, 2.5 at an angle of 135 degrees, also given in volts. Now, hopefully you remember from our phasor video that we actually cannot just add these up directly. We need to convert them. So these guys are in polar form. Blah. We need to get it into rectangular form so that we can add it, and then we have to convert back to polar form. So it's a little bit tedious, but not that complex. So we'll start things off. It's just 5 times the cosine of 45 degrees plus J times 5 times the, not sine, not cosine. Excuse me. 5 times the sine of 45 degrees plus, now 2.5 at 135 degrees is 2.5 times the cosine of 135 degrees plus J times 2.5 times the sine of 135 degrees. Now if we go and crunch up these numbers in the calculator, we get V is equal to 3.5 plus J 3.5 plus actually negative 1.8 plus J 1.8. No. Yeah. J 1.8. We'll combine some like terms. We'll get that it's 3.5 minus 1.8 plus J times 3.5 plus 1.8. And that'll give us a final answer in rectangular form. V is equal to 1.7 plus J 5.3 volts. And of course, we need to give it as a polar form phasor. So one last step here, we'll say that V is equal to, remember the amplitude is just the square root of the sum squared, the square root of the square of the sums, 1.7 squared plus 5.3 squared at an angle of the inverse tangent of the imaginary component 5.3 over the real component 1.7. So that'll give us, after all of that mess, a final answer. V is equal to 5.6 at an angle of 72 degrees, and that is in volts. The last part here, the last part of this example says, hey, what's the voltage as a steady state sinusoid? Steady state sinusoid. And we actually have everything we need for that, right? Remember that our steady state voltages are given as Vm times the cosine of omega t plus phi degrees in volts. We know that, remember, omega was 1,000 way back up there at the top. And so we'll get that our V sub t is equal to, Vm is just 5.6, we've got that in the phasor, times the cosine of 1,000 t plus 72 degrees. And that is given in volts. And there you have it, all the way from the top. We're finally doing some work on circuit elements. We had this circuit here, 100 ohm resistor in series with a 50 millihenry inductor and a current of 50 cosine 1000 t plus 45 degrees milliamps. We found the impedances of the resistor and the inductor. We found the voltage drop across the resistor and the inductor. We found the voltage drop across the entire circuit by summing them up. And then we finally found that steady state voltage. So there you have it. As always, if you have any questions, comments, concerns, please let me know. And if not, I look forward to seeing you guys in the next video. Thank you.